Hello everyone, good evening. Today we are going to learn about how to simulate the NACA 0012 aerofoil or any other type of the aerofoil in the Fluent software. So we'll start with the getting the coordinates of the this aerofoil, and then we will import to the design molder. After that we will create the hexa mesh, and we will keep the y plus 1, and then we simulate in the with the appropriate settings for the solver and the boundary conditions in the Fluent, and then we will compare the data with the experimental, and then we will conclude about the different turbulence models as well. So let's start with here. So first, the step one would be the to get a geometry or the points or coordinates of the aerofoil. Through equation you can use the Excel, or you can directly find out these calculators on the internet, and then we arrange in the particular order which can be, we can read that one in the design modeler. So to uh, get this order or this format, we will use Excel, and once we have made them in a way the design modeler can read, we will import to the design modeler, and then we will create a hexa mesh, and we will calculate the first cell distance based on the y plus should be less than 1 from some online y plus calculator, and then we will go to the Fluent and we will import the mesh, and here we will set the boundary conditions, solver, and we run the simulation, and once the solution is converged we will post process in the Fluent or in the Excel. Let's start with the step number 1 to get the geometry. So here's the aerofoil. You can just put the camber 0 and thickness 12%. If you plot this one, so now we have the NACA 0012 aerofoil, and you can increase the number of points as well, 20 to 200, and also the edge trailing edge can be closed, or the by the closed trailing edge means we have the sharp trailing edge, so something like this. This is the closed trailing edge. It can be round, but anyhow if you generate through this website, the trailing edge you will get will be the of the sharp type. And the second one is the closed trailing edge, also open. Second is the open trailing edge, which is the natural way the aerofoil are drawn, where you will end up with the like this. So there's a 1 point over here and this is 1 point over here, and then you have to close this one in the some geometry tools. So for the both processes, for the both type of aerofoils, we have a different format in which we can read the coordinates into the design molder. So I will show you how to do this thing. So from here we can plot them for the both aerofoils. So I just copied them for the both cases and same number of points into Excel sheet, these points, and both aerofoils are overlapping each other, but in the open type of the aerofoil does not converge to single point, but in the case of closed it converges to the a single point, and you will get the sharp trailing edge. So these are points, total 81 points coordinates, and you can see in the open-ended aerofoil the endpoints are different. They are apart by the distance 0.00126, and here it's a point minus 0.0013, but here the endpoint start point is the same. And here is the template for the this design modeler file. So we will follow this template. First one will be the group. If there are the more curves, so we can group with number 1, 2, 3, and for each group we have the corresponding XYZ coordinates. Even the aerofoil has the no Z coordinate, then but you have to put the 0 value instead of the you cannot leave the that column blank, so you have to put something. So if there is no value, then you put the 0 value for the Z coordinate, and here is the sequence of the point. So you put the 1, 2, 3, and it's up to the 6 points over here. and after that, uh, but for our case the number of points are 81, and so I have arranged these aerofoil coordinates, the format I have shown you over here, and this is the for the open-ended. We put all the points, we number them, but for the closed-ended aerofoil, for the last point, we know that the last point is same as the first point, as I've shown you over here. So to instruct the design modeler that the last point is the same point, is the same as the first point, we just put the, instead of 81 we put the 0, and we will not put any value for the coordinate. So it will take the coordinates of the first point. So now we will go to the design modeler. Although we have solved all the cases, but here I will show you from the zero how to do these steps in the design modeler. So I will just double click on the geometry icon. Here choose any plane. So because all points are in the xy plane, so just click on the look at, and from here, from the concept menu, just draw the choose the 3D curve, and here you have the let's say coordinate units, so it's going to meters, and coordinate file we can get directly from the point selection if you have the points over here, or we can have the from the coordinate file. So just locate the file. So we have the both files over here. I just copied these points into the text file, simple text file. If I open over here, so you can notice we have the same thing just copied in the simple text editor. This is for the closed end, we have 0 point, and for the second case we have for the open-ended, we have both points are not are the same, both points are not same, so we have 81 point has the same some other coordinate. So just close them, and you can open any file from here. So just click on generate button, and we have the aerofoil with us. You can hide the cross section alignments, and you can also hide the frozen body transparency, and you can put the black color on the aerofoil. This is the first case, we have the sharp tailing edge, and you can replace the file, and we can have the this close-ended file, this open-ended file. You can generate, and just from the view you can display the vertices. So now these both vertices are at the different location in the along the y-axis, and after that we are going to create the I will show you all steps for the this closed end or the sharp tailing edge case. So we are going to put some domain over around this aerofoil. From the sketch menu, I am going to choose the rectangle, and put it some dimensions. Maybe we are going to put the 15 chord length upstream, so it's a 15. you can modify and you can drag the rectangle around the aerofoil in this way. Okay, and also we can put a dimension for the upper side length, also in the minus y axis, also for the downstream condition. Okay, for downstream condition I'm going to put the 25 times, and for the vertical 15 same as the upstream condition. So now we have defined our domain as well. Now I will go to the modeling, and here I will choose the surfaces from sketches. So I will choose the sketch number 1, click on generate. I just generated the my geometry with the help of the from this sketch. Also I will generate the surface from edges for this aerofoil, and since it's a closed type of aerofoil, so we don't need to select the another edge. It's only single edge over here, so click on generate. So now we have the 3 bodies, 2 surface body, 1 line body. You can surface a line body and then just go to the create, and here use the boolean operation and choose the operation as a subtract. The target body is a far field, and we are going to cut the this aerofoil body from this target body, which is a far field. The tool body is going to be the aerofoil. Just click on these planes and you can choose the aerofoil easily. Just click on generate. Now this aerofoil has been separated from the main domain. So, and you can put the name for these conditions. Let's say for the inlet you can put the in, and generate. For the upper boundary you can say upper boundary, and for the bottom boundary you can call this one as the bottom, and the outside boundary or the out boundary. And also for the aerofoil we will call this one as the just aerofoil. Generate, and after that I am going to drop the ICM CFD on the geometry, and make sure that when you are working, so just see the properties of the this one, that this should be set to the 2D. It's very much important. Maybe you can delete the ICM CFD and drop again, so that it will get the understanding that the now geometry is 2D, so it's going to create the 2D mesh as well. Okay, since we are simulating this flow for the Reynolds number of the 3 million, which is the case over here, although for all Reynolds numbers at 0 angle of attack the drag coefficient is same. You can see from here, so 0 angle of attack we have the 0 lift, because the NACA 0012 symmetrical aerofoil, so definitely at the 0 angle of attack we have the 0 lift coefficient. So for the all Reynolds numbers we have the same drag coefficient, which is approximately equal to the 0.006. And secondly, we are simulating this flow at 3 million Reynolds number, So from this information we can calculate the velocity at the inlet of the geometry. So let's say Nernst number is 3 million and density is 1.225 and viscosity is 0.4017894. It's available in the Fluent database as well, and the chord length is a 1 meter. So from here we can calculate the Nernst number, because the definition of Nernst number is that Re is equal to density, velocity, length upon viscosity. So from here we can calculate the velocity as Nernst number, the viscosity, density upon length. So it comes out to be the around 43.82 value. So from here we can go to the some calculator side where we can calculate our y plus distance. So it's y plus calculator. You can find out this one on the CFD online. So I will just put the values. So free stream velocity is equal to the 43.8882. Density is 1.225 and the dynamic viscosity is 1.78 7894 e power minus 5, and the chord length is 1 meter and the y plus required is 1. So from here we can estimate this is going to be the 8.5 into 10 power minus 6, which is we can put in the ICM CFD. So first we create the 2D blocking. We can call this one as a fluid. It's going to be the 2D pinner block. We can turn on the points over here and we can check these boundary conditions. Okay, so we can associate them one by one, or we can associate them using the auto associate, and they all will be associated to the corresponding entities in a one single command. After that, you can have the different shape of the domains. For the different angle of attacks, the best solution would be to use the some sort of the semicircular inlet domain. So we are going to so we can change the inlet domain in the design modeler again. So from here we can choose the 3-point arc, or it can be center and the 2 points. So we can choose these 2 points. Okay, then we can use the constraints. We can make them the tangent. Okay, then we can delete the extra edges using trim command. Just click on generate. Okay, over here we can change the name for this boundary. So this is going to be the inlet. Generate, and we can delete these two boundaries, and the outlet is going to same, and aerofoil over here. Just save the project. So just click on the update option, and we can have the modified geometry with the circular inlet domain. Okay, now we can use again the same tool, and we can update the association. And we can associate these two vertices to the curve as well, and these three edges to these three curves, and also we can associate the vertex to the point. Just we can create the new part with for the points. Just turn off all other options, just keep the points option on, and select all the points, so we can associate them with a point. And then you can use the snap vertices option. Okay, now just create a O-grid block and choose the edge at the outlet and apply. Just move these edges towards the aerofoil in a very rough way. Okay, and then we'll make another split over here, and then we will use the collapse blocks, and we use this edge, and we will collapse the block in the far field, just in the back region of the aerofoil. Just set again the blocking. Here we can use the set location option. We'll use before that we are going to associate this one to the point, and also we are going to associate these three edges to this curve. Also I'm going to create one point at the 50% location, which is going to be on the leading edge, and I can then after that I'm going to split the edge into two parts. Again I will create a point at the 0.95 or 0.05 location, whatever the appropriate for this one. So now for this side we are going to use the 0.05. So initially I'm going to associate these vertices to these points, but then I will associate them to the curve, because I don't want to fix them at this location. So if we associate these two vertices to the points, now this location will be fixed. but if we associate them to the some curve, we can move them on around the curve or on the curve. So this is how we are doing it. Okay, now we have set all the things, so now we can set a location also for the other vertices. So for this one, for this part I am going to move in the y direction, apply, and for these two vertices I will move the its x location. And for the O-grid around the geometry aerofoil, I am going to put the another O-grid by the using the just split option, and then I am going to put the some rough mesh size, maybe 0.5, accept. On the aerofoil, maybe I am going to put the 0.01 or 0.005, apply. Just check the mesh size. It looks like very good mesh size for this type of the geometries. Okay, I'm going to also create another part for the solid part, which is going to be the domain or the block inside the aerofoil. We'll just hide this one. Now I'm going to set the size on the towards the aerofoil and select the geometric tool and put the sizing on the spacing tool. Is going to be the 0.50 point and 5 zeros and 85. So it's 1 2 3 4 5 and the 85. Number of nodes I'm going to put 60, and the ratio by which I'm going to expand the these things is 1.15. Also I will copy all the parameters to all the parallel edges. So just right click on the pre-mesh and recompute, and I also need to change the number of points on the aerofoil. Maybe 80 points are enough. On the leading edge 30 points, in the far field maybe 100 points. I need to check the also location for the this one, so I am going to put the geometric one, and the ratio is going to be 1.2. Recompute, and for the block in the just after this O-grid, I am going to get the size from these edges. I will use the mesh edge spacing, and once it's a mesh, I am going to use this size, and I will use again the geometric tool, and the ratio is going to be the 1.2 as well. Apply and recompute. Okay, now right click on pre-mesh and convert to the unstructured mesh, replace, and in the output panel we can set the boundary conditions for solver and the boundary conditions for the inlet. We can choose the velocity inlet, and for the outlet we can choose the pressure outlet, and for the aerofoil the wall condition. Okay, then we can export the mesh, but this mesh should be in the 2D or two-dimensional mesh. So done. Okay, now I will use my already available cases, the same thing, same mesh, same procedure. So I'm going to show you how we can set up the problem for the different cases. Here we have set these cases for the different turbulence models. So for example, for the KL omega model, which is the transition model, so same y plus 1 mesh is there. I'll just show you how we can set the different steps. First go to the model, and we are going to set the turbulence model. You can set any model. It can be inviscid, spiral aluminous, K epsilon, K omega, transitional model, 6 equation model, or non-stress model. So just click on OK. And in the material, we are going to set the only density and the viscosity. So by default for the air we have these properties. Just click on the close. In the boundary conditions, we are going to set the velocity, which we have calculated, which is 43.822, and no need to set anything else, because 0 is the degree of 0 degree angle of attack. So you can put any value, but normal to the boundary, or it can be x component of the flow direction. Okay, and solution method should be the coupled, and for the initial solution you can change them to the first order, so the solution can proceed without any conversion issues. Solution control, you can put the current number 200 in the first, and then you can increase them to the 2 leg. It depends upon solution, and you can initialize the solution from the far field and initialize, and then we can auto save the file. We can retain the few copies and then run the calculation. The benefit of using the coupled solver as compared to the segregated solver is that we can get the solution in very few iterations. As you can see, the CD curve has converged from the very high value, and it converged to the almost to the value we required them. So it is almost close to those values. So once the solution is converged, we can close the this one, and we can proceed to our results, which are over here. You can go to the reports, and here you can click on the forces, and you can check the forces. In the x direction, it's going to be the drag coefficient, so you can copy this one. I will copy for the other case, which is converged case. So for example, for the 6 equation model, just go to the reports and the forces, print. So it's going to be the 0.0059. It's almost the 0.006, which is same as the we get the value from the experiment. You can see again here. If you have any questions or any query, you can email us at the farcfd@gmail.com, or you can add us at the farcfd, and you can have the Skype call or Skype chatting. Thank you for your time. Good night.